In the fifth lecture, we will learn the sampling methods, the sampling bias, and the sampling distribution. Sampling is the selection of a sample of individuals from a population for inference. There are two types of sampling: probability sampling and non-probability sampling. Probability sampling is a sampling technique based on the theory of probability with the random selection. Random selection may help us to create a sample as a good representation of the population and reduce the bias. On the contrary, non-probability sampling does not involve random selection and has a higher risk of sampling bias. Now we introduce some commonly used probability sampling methods. The first is the simple random sampling. The method guarantees that each subject in the population has an equal chance of being chosen, and the sample is chosen entirely by chance. This method is simple, but may not be practical if the population is very large because the method requires a sampling frame that provides a list of all individuals in the population. For example, if we need to estimate the average adult height in the US, then we need a list of all adults so that we may choose from. Obviously, it may be very difficult to get such a sampling frame. We discussed random sample in the last lecture. Does simple random sampling generate a random sample? Typically, simple random sampling selects the subjects without replacement. If we select a subject during the first selection, then the selected one will be removed from the population, and we are not able to select it again. Thus, the selections are dependent, as we discussed in the hat example in lecture 2. So, strictly speaking, we may not have a random sample. But if it samples with replacement, then it is a random sample. On the other hand, the difference is practically insignificant for very large populations. Thus, in most cases, we may ignore the difference and treat the sample as a random sample. The second method is stratified sampling. First, we divide the population into groups as strata, then randomly select subjects from all strata groups. The key for this method is we make strata groups as heterogeneous as possible, and we must select from all strata to include the heterogeneity. In the last adult height example, gender is a good strata variable because the male height may be different from the female height. The stratified sampling could be layered. For example, age could be the second layer strata variable. Cluster sampling is another popular sampling method that should not be confused with the stratified sampling. In the cluster sampling, we divide the population into many clusters and then randomly select clusters and take all units in the selected clusters to form the sample. Different from the strata sampling, the cluster groups should be as homogeneous as possible so that each cluster is a good representation of the population. Now let's check some examples. A bank randomly selects 10 workdays last year and find all approved loans in those days. What is the sampling method? It is a cluster sampling because we don't expect loans approved one day are much different from another day. The cluster variable is the date. Next, a school agent assigns a unique number to every student in a school roster and randomly select 100 numbers from all numbers and form a sample of 100 students assigned to those numbers. This is a simple random sampling method because all students have the equal chance of being chosen. In the third case, we randomly select 50 male students and 50 female students from a group of 10,000 students. Clearly, this is a stratified sampling using gender as the strata variable. Sampling bias results in a biased sample. The biased sample may not represent well the population. Convenience samples and volunteer response samples are common biased samples generated by non-probability sampling methods. However, even probability sampling methods may generate biased sample if the selected sample fails to represent the whole population. Let's take a look at the examples in the last slide. First, a bank randomly selects 10 workdays in the last year and finds all approved loans in those 10 days. This is the cluster sampling. Let's say the bank would like to investigate loans in all U.S. states. However, its organic loan data are all from North Carolina state. Thus, the bank may fail to make inference on all U.S. loans based on its organic loan data. In this case, we may have bias due to underrepresentation. The loans from North Carolina may not be a good representation of the loans from other states. The second case, select 100 students from a school roster. It is simple random sampling. Let's say the school agent is interested to survey the undergraduate students for their satisfaction with the school facilities so that they randomly select the students from a roster, a list of all students, which include both undergraduate students and graduate students. Thus, we may have bias due to overrepresentation because the graduate students may have different focus in the facilities from the undergraduate students. Third, randomly select 50 male students and 50 female students from 10,000 students. This is the stratified sampling. Let's say the population of those 10,000 students has 1,000 male students and 9,000 female students. Then the sampling may have bias due to inappropriate representation. The sample adds more weights on male students by enforcing the same amount of male and female students. Most often, the sampling bias is generated by non-probability samples such as convenience samples and volunteer response samples. But from these examples, we learn we may still have the sampling bias even we use probability sampling methods if the sample is not a good representation of the population. The sampling distribution is a probability distribution of a statistic obtained from all possible samples from the population. It is a distribution of a statistic based on random samples. There are two keys in this concept. First, the sampling distribution is a distribution of a statistic. For example, the sampling distribution of the sample mean is the distribution of all sample means from all possible samples of size n. Here, the statistic is the sample mean. The sampling distribution of the sample mean is so commonly used that if there is no indication of the statistic, the sampling distribution usually means the sampling distribution of the sample mean. Second, the sampling distribution is not from one sample, although we may only have data from one sample. Instead, it is from all possible samples. Here we need to distinguish the sample distribution and the sampling distribution. The sample distribution is the distribution of one random sample, but the sampling distribution is based on all possible samples from the population. Often, the sample distribution is not as useful as the sampling distribution in inference. From the last lecture, we learned that the expectation of the sampling distribution of the sample mean is equal to the population mean, which suggests that the sample mean is an unbiased estimator of mu. The standard error of a statistic is the standard deviation of the sampling distribution of a statistic. Again, in many cases, the standard error may suggest the standard error of the sample mean unless indicated otherwise. Now, let's derive the formula of the standard error for a random sample of size n. The variance of the sampling distribution of the sample mean is the variance of y bar. Here, x is defined as the sample sum. Using the variance properties we learned in lecture 2, the variance of the sampling distribution is this. Since all random variables are independent, the variance of the sample sum is the sum of all variances. Since they are identically distributed, the variance of each random variable is the same, which is sigma squared. Thus, the variance of the sample mean is the population variance divided by the sample size n. The standard error of the sample mean is the standard deviation divided by square root of n. The results tell us that the variance of the sampling distribution is largely affected by the sample size n. The variance of the sampling distribution is inversely proportional to n when the population variance is known. In the next lecture, we will learn why the sampling distribution of the sample mean is important and how we use the sampling distribution instead of the joint distribution to make inference. In summary, we learned the sampling methods, the sampling bias, and the sampling distribution. Random selection may help us to form a probability sample and reduce the bias. The simple random sampling guarantees that each subject has an equal chance of being chosen, and the sample is chosen entirely by chance. The stratified sampling divides the population into strata and randomly selects subjects from all strata. All strata should be as heterogeneous as possible. The cluster sampling divides the population into many clusters. Randomly select the clusters and take all subjects in the selected clusters to form the sample. All clusters should be as homogeneous as possible. Sampling bias results in a biased sample that may not represent well the population. Non-probability sampling methods, such as convenience samples and volunteer response samples, are prone to generate biased sample. If the selected sample fails to represent the whole population, then even probability sampling methods may generate biased sample. The sampling distribution is the probability distribution of a statistic obtained from all possible samples drawn from the populations. The statistic may differ from one sample to another sample. Thus, the statistic is also a random variable. The standard error of a statistic is the standard deviation of the sampling distribution of a statistic. For example, the standard error of the sample mean is the population standard deviation divided by the square root of n.